Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where ancient stars have completed their long, peaceful journeys and settled into their final, serene forms. In the quiet space of the universe, we find ourselves drawn to one of these stellar remnants, a white dwarf star, glowing softly like a cosmic ember in the darkness. Gently, we discover that white dwarfs are among the most fascinating objects in our universe. Yet they whisper their secrets in the softest of cosmic voices. Like whispers in the night, these stellar remnants tell stories of transformation, of matter compressed into forms so dense that a teaspoon would weigh as much as an elephant. Yet they do so with a peaceful radiance that has been shining steadily for billions of years. As our journey continues into this contemplative exploration, we'll drift alongside a hypothetical traveler. Perhaps it's you. Perhaps it's simply a consciousness floating through space as they approach, and eventually fall into one of these remarkable stellar objects. But fear not, for in the realm of the sleepy scientist, even the most extreme cosmic phenomena become gentle teachers, offering us profound insights into the nature of matter, energy, and the peaceful processes that govern our universe. Let's drift into the story of what happens when something falls into a white dwarf, beginning with understanding these serene stellar remnants themselves. In the quiet space of stellar evolution, most stars like our Sun will one day shed their outer layers in gentle, cosmic breaths, leaving behind their cores as white dwarf objects roughly the size of Earth, but containing the mass of an entire star. White dwarfs represent one of the most peaceful endpoints in stellar evolution. Unlike their more dramatic cousins neutron stars and black holes, white dwarfs settle into a long, quiet existence, cooling slowly over trillions of years. They are supported not by the nuclear fusion that once powered their parent stars, but by a quantum mechanical effect called electron degeneracy pressure, a phenomenon that gently pushes back against gravitational collapse. In the contemplative silence of space, our white dwarf glows with a soft, white light. Its surface temperature still remarkably hot, around 5,000 to 50,000 Kelvin, yet it radiates this energy peacefully into the cosmic void. The surface gravity is intense, about 100,000 times stronger than Earth's, yet from our distant vantage point, it appears as nothing more than a gentle, distant star. Now we float toward our thought experiment, imagining what it would be like to approach this stellar remnant. Our hypothetical traveler begins their journey from a comfortable distance, perhaps several astronomical units away, far enough that the white dwarf appears as just another point of light against the star-filled darkness. At this distance, space feels familiar and peaceful. Our traveler drifts in the cosmic silence, surrounded by the gentle radiation pressure from distant stars, and the barely perceptible whisper of solar wind from the white dwarf itself. The temperature here is cold, approaching the cosmic microwave background temperature of 2.7 Kelvin, just a few degrees above absolute zero. As our journey continues, we begin to appreciate the remarkable nature of what lies ahead. This white dwarf, despite its small size, contains the gravitational memory of an entire star. It has compressed the mass of something like our Sun into a sphere roughly the size of Earth. The implications of this compression whisper to us across the void, suggesting that extraordinary things await our gentle traveler. Let's drift into a deeper understanding of the physics that governs white dwarfs. In the quiet space of quantum mechanics, these objects exist in a state of perfect balance between two fundamental forces. Gravity, that gentle but persistent force that shapes the cosmos, pulls inward, trying to compress the white dwarf further. But electron degeneracy pressure pushes outward with equal strength, creating a stable equilibrium that can last for trillions of years. This electron degeneracy pressure arises from the Pauli exclusion principle, one of the fundamental rules of quantum mechanics. Like whispers in the night, electrons in the white dwarf's interior communicate through quantum fields, ensuring that no two electrons can occupy the same quantum state. As gravity tries to compress the matter further, electrons are forced into higher and higher energy states, creating an outward pressure that perfectly balances the inward pull of gravity. Gently, we discover that this quantum mechanical support makes white dwarfs remarkably stable objects. Unlike planets, which are held up by electromagnetic forces between atoms, or main sequence stars, which are supported by the outward pressure of nuclear fusion. White dwarfs rely on the fundamental quantum nature of matter itself for their structural integrity. As our hypothetical traveler continues their peaceful approach, they begin to notice subtle changes in their environment. The gravitational field of the white dwarf, while still weak at this distance, starts to influence their trajectory. Rather than falling straight in, they follow a gentle curved path, their motion governed by the same laws that guide planets around stars and galaxies. Through the cosmic web, in the quiet space of Einstein's general relativity, we understand that this curved motion isn't due to a force in the classical sense, but rather to the curvature of space-time itself. The white dwarf's mass creates gentle ripples in the fabric of reality, and our traveler simply follows the most natural path through this curved landscape. Now we float toward a more detailed examination of the white dwarf's properties. As stellar remnants go, white dwarfs are remarkably diverse. Some are composed primarily of carbon and oxygen, the ashes of helium burning in their progenitor stars. Others contain heavier elements like neon, magnesium, or even iron, depending on the mass and evolution of their parent star. The surface of our white dwarf is a study in peaceful extremes. Despite having a temperature that would vaporize any known material in an instant, the surface appears relatively calm. Like whispers in the night, the white dwarf's magnetic field permeates the space around it. Many white dwarfs possess magnetic fields millions of times stronger than Earth's, yet these fields extend into space with a gentle elegance, creating invisible structures that guide charged particles in complex, beautiful patterns. As our journey continues, our traveler begins to feel the first subtle effects of approaching this stellar remnant. At a distance of perhaps 1 astronomical unit, roughly the distance from Earth to the Sun, the white dwarf's gravitational field becomes more pronounced. Tidal forces, those gentle differential pulls that shape ocean waves on Earth, begin to make themselves known. But let's drift into understanding these tidal forces in their most peaceful context. Rather than violent stretching or compression, we can imagine these forces as the universe's way of gently reshaping matter as it encounters different gravitational environments. The tidal force rises because gravity follows an inverse square law. The closer you are to a massive object, the stronger the gravitational pull becomes. In the quiet space of physics, this means that if our traveler is extended in the direction of the white dwarf, the part of them closest to the star experiences slightly stronger gravity than the part farthest away. This differential creates a gentle stretching sensation, like being slowly drawn out by invisible hands. At this distance, these tidal effects are still subtle, perhaps comparable to the tidal forces we experience from the moon here on Earth. Our traveler might notice a slight sensation of being stretched, but nothing uncomfortable or alarming. Instead, it is more like floating in a cosmic ocean where gentle currents tug at different parts of their being. Gently, we discover that these tidal forces also affect time itself. According to Einstein's theory of general relativity, time passes differently in different gravitational fields. As our traveler approaches the white dwarf, time begins to run slightly slower relative to distant observers. This gravitational time dilation is a peaceful reminder of the intimate connection between space, time, and matter. From the perspective of someone watching from far away, our traveler's clocks would appear to tick slightly slower. Their movements would seem to become more leisurely, their speech would deepen in pitch, and their entire existence would appear to unfold in a gentle, dreamlike slow motion. But from our traveler's own perspective, nothing seems different. Their watches tick at the same rate, their thoughts flow at the same pace, and their perception of time remains unchanged. This is one of the beautiful subtleties of relativity. Each observer experiences their own time as normal, while noticing that distant clocks behave differently. As our journey continues deeper into the white dwarf's gravitational embrace, let's drift into contemplating the changing view of the universe around our traveler. As they fall inward, the white dwarf begins to dominate their view, growing from a distant point of light to a noticeable disk, and eventually to a blazing sphere that fills an increasingly large portion of the sky. The view behind them toward the rest of the universe begins to change as well. Due to gravitational lensing, the white dwarf's gravity bends light rays passing near it, creating subtle distortions in the appearance of background stars. Like looking through a cosmic lens, the stellar patterns shift and warp, creating new constellations that exist only for observers in this particular gravitational environment. In the quiet space of this altered perspective, our traveler witnesses one of the universe's most beautiful optical effects. Light from distant galaxies, bent by the white dwarf's gravity, creates multiple images of the same objects. Some stars appear to have halos or rings around them, while others seem to dance in slow, stately patterns across the sky. Now we float toward understanding the thermal environment our traveler encounters. Despite the white dwarf's surface temperature of tens of thousands of Kelvin, space around it remains surprisingly cold. The vacuum of space provides excellent insulation, and only direct exposure to the white dwarf's radiant energy would provide significant heating. At distances of several astronomical units, our traveler experiences temperatures only slightly above the cosmic microwave background. The white dwarf's energy output, while impressive, is spread over such a vast area that its warming effects are gentle and gradual. It's like sitting near a very hot but very distant campfire. You can feel its warmth, but it doesn't overwhelm you. But as our traveler continues their inward journey, this thermal environment begins to change. The intensity of radiation follows the same inverse square law as gravity, meaning that as the distance to the white dwarf halves, the energy received quadruples. This creates a gentle but steady warming that our traveler would notice as a gradual transition from the cold of deep space to increasingly warmer conditions. Like whispers in the night, the white dwarf's radiation carries information about its composition and structure. The spectrum of light it emits tells a story written in the language of atoms and molecules. Hydrogen lines, helium signatures, and traces of heavier elements paint a picture of the star's evolutionary history and current state. As our journey continues, let's contemplate the increasing effects of the white dwarf's gravitational field. At a distance of 0.1 astronomical units, about 1/10 the distance from Earth to the Sun, the gravitational effects become much more pronounced. Tidal forces, while still manageable, begin to create noticeable stretching sensations. Our traveler might feel as though they're being gently pulled in the direction of the white dwarf, with their feet assuming their oriented feet first toward the star, experiencing slightly stronger gravity than their head. This differential amounts to perhaps a few % difference in gravitational acceleration, noticeable, but not overwhelming. In the quiet space of this stronger gravitational field, time dilation effects also become more pronounced. Clocks would now run noticeably slower compared to those in the outer solar system. A day measured by our traveler's watch might correspond to slightly more than a day, as measured by distant observers. This time dilation has profound implications for our traveler's perception of the universe. Light from distant stars appears slightly blue-shifted as it falls into the gravitational well alongside our traveler, while light trying to escape the white dwarf's vicinity appears red-shifted. The universe takes on a subtly different hue, with the colors of space itself shifting in response to the curvature of space-time. Gently, we discover that the white dwarf's rotation, if it has any, begins to influence our traveler's trajectory. Many white dwarfs spin rapidly, some completing a full rotation in just a few minutes. This rotation drags space-time itself along with it, creating an effect called frame dragging or the lens-stirring effect. This dragging of space-time is like stirring honey with a spoon. The rotation of the massive object creates gentle currents in the fabric of reality itself. Our traveler, following the natural paths through curved space-time, finds their orbit slowly precessing around the white dwarf, tracing out complex, beautiful patterns in space. Let's drift into understanding the magnetic environment surrounding our white dwarf. As mentioned earlier, many white dwarfs possess incredibly strong magnetic fields, sometimes millions of times stronger than Earth's magnetic field. These fields create invisible structures in space, shaping the behavior of any charged particles in the vicinity. If our traveler has any electric charge, perhaps from cosmic ray interactions or the photoelectric effect caused by the white dwarf's intense radiation, they would begin to feel the influence of these magnetic fields. Charged particles follow helical paths around magnetic field lines, creating elegant spiral trajectories that add another layer of complexity to our traveler's journey. In the quiet space of electromagnetism, these magnetic fields also affect the white dwarf's appearance. The intense magnetic fields can split spectral lines through the Zeeman effect, creating multiple, closely spaced absorption or emission features in the star's spectrum. This splitting tells astronomers about the strength and structure of the magnetic field, adding another voice to the cosmic symphony of information carried by light. As our journey continues inward, the radiation environment becomes increasingly intense. At 0.01 astronomical units, about 1.5 million kilometers from the white dwarf's surface, our traveler encounters radiation levels millions of times stronger than sunlight at Earth's orbit. Yet even this intense radiation has a peaceful quality to it, representing the gentle outpouring of energy from the white dwarf's hot surface. This radiation consists primarily of visible light and ultraviolet photons, the peaceful exhalation of a star that has found its final equilibrium, unlike the chaotic, violent radiation environments around black holes or neutron stars. The white dwarf's radiation is steady, predictable, and beautifully uniform. The intense radiation at this distance would quickly heat any ordinary matter to thousands of degrees, but in our contemplative thought experiment, we can imagine our traveler as somehow protected from these thermal effects, allowing them to observe and experience the journey without harm. Now we float toward understanding what happens as our traveler approaches the white dwarf's surface. At distances of just a few white dwarf radii, perhaps 10,000 to 20,000 kilometers above the surface, the gravitational environment becomes truly extreme by terrestrial standards, yet maintains its peaceful, inexorable character. The surface gravity of our white dwarf is now comparable to what our traveler would experience if they were compressed down to the size of a marble while retaining their original mass. Every atom in their body would feel a gravitational pull 100,000 times stronger than what they experienced on Earth, yet this immense force manifests as a gentle, constant acceleration toward the stellar surface. Tidal forces at this distance become substantial. The gravitational gradient, the rate at which gravity changes with distance, creates stretching forces. That would be quite noticeable if our traveler is oriented radially, feet pointing toward the white dwarf. Their feet would experience gravity perhaps 10% stronger than their head, creating a gentle but persistent stretching sensation. In the quiet space of general relativity, these extreme gravitational conditions create equally extreme time dilation effects. Time now passes significantly more slowly relative to distant observers. What feels like minutes to our traveler might correspond to hours as measured by clocks. Far from the white dwarf's influence, the visual effects at this proximity are remarkable. The white dwarf fills a large portion of the sky, its brilliant surface glowing with the heat of tens of thousands of degrees. The curvature of space-time becomes visually apparent as light rays bend around the massive object, creating a sense of looking down into a cosmic well or valley in the fabric of reality itself. Like whispers in the night, the white dwarf's surface reveals subtle details at this close range. The photosphere, the layer from which light escapes, might show gentle variations in brightness or color, perhaps indicating magnetic field structures or compositional differences. The limb of the star, where our line of sight becomes tangent to the surface, appears darker due to the decreased optical depth, creating a gentle gradation from brilliant center to darker edge. As our journey continues even closer, let's contemplate what our traveler observes about the white dwarf's immediate environment. Some white dwarfs are surrounded by thin atmospheres of hydrogen or helium, the remnants of material that has settled back onto the surface from the surrounding space. These atmospheres are incredibly thin by terrestrial standards, but become noticeable at such close range. The interaction between the white dwarf's magnetic field and any surrounding plasma creates beautiful, complex structures. Charged particles spiral along magnetic field lines, creating glowing threads and sheets that dance in the intense radiation environment. These magnetospheric phenomena are like cosmic aurora, painting the space near the white dwarf with gentle, shifting patterns of light. Gently, we discover that some white dwarfs pulsate with regular periods, their surfaces rising and falling like the gentle breathing of a sleeping giant. These pulsations, caused by acoustic waves trapped within the star's interior, create subtle variations in brightness and surface temperature that propagate across the stellar surface in beautiful, wave-like patterns. Our traveler, now just thousands of kilometers from the surface, experiences gravitational effects that would seem impossible by everyday standards. The curvature of space-time is so pronounced that parallel light rays converge noticeably. Over short distances, the geometry of space itself has become non-Euclidean in ways that are directly observable. Time dilation has reached extreme levels. Our traveler's clocks, as viewed by distant observers, would appear to be running in slow motion. Paradoxically, from our traveler's perspective, the rest of the universe appears to be speeding up. They would see distant stars evolving more rapidly, galaxies spinning faster, and a cosmic microwave background radiation blue shifting to higher frequencies. Now we float toward the final stages of our traveler's journey. As they approach within a few hundred kilometers of the white dwarf's surface, the tidal forces become overwhelming by any normal standard, yet we can contemplate them as the universe S-wave gently, reshaping matter to match the extreme conditions of this environment. The gravitational gradient at this distance means that our traveler S-feet experience substantially stronger gravity than their head. This differential stretching force, known as the tidal force, begins to overcome the electromagnetic forces that normally hold matter together. In peaceful, inevitable steps, our traveler begins to be transformed by the white dwarf's gravitational embrace. This transformation is not violent or sudden, but rather a gentle yielding to fundamental forces. The bonds between atoms, which seem so strong in our everyday experience, prove to be weak compared to the tidal forces generated by the white dwarf's gravity. Our traveler begins to stretch, their form elongating in the direction of the gravitational field. In the quiet space of this transformation, we can contemplate the profound physics at work. The electromagnetic forces that create chemical bonds and give matter its familiar properties are being overwhelmed by gravitational forces, a rare occurrence in the universe. That only happens in the vicinity of extremely dense objects like white dwarfs, neutron stars, and black holes. As our journey continues through these final moments, our traveler experiences what physicists call spaghettification, though we prefer to think of it as a gentle reshaping by cosmic forces. Their form elongates, becoming thinner and longer as the tidal forces stretch them along the radial direction, while compressing them in the directions perpendicular to the gravitational field. This process happens gradually, almost meditatively, as our traveler falls through the final kilometers toward the white dwarf's surface. Each moment brings them deeper into the gravitational well, where space and time themselves take on properties that would seem magical to observers. In less extreme environments, the white dwarf's surface now fills virtually their entire field of view. The brilliant, white-hot photosphere extends in all directions like a cosmic ocean of light. The temperature of this surface, perhaps 20,000 Kelvin or more, represents the stored thermal energy of a star S-form nuclear core, now slowly radiating away over cosmic time scales. Let's drift into contemplating what happens when our traveler finally reaches the surface. The white dwarf's surface gravity is so intense that the escape velocity, the speed needed to escape from the surface, is several thousand kilometers per second, a significant fraction of the speed of light. Our traveler, having fallen from far away, approaches this surface at tremendous velocity. The impact with the surface is almost instantaneous from our traveler's perspective, yet it represents the culmination of a journey through increasingly curved space-time. In a sense, our traveler doesn't really hit the surface so much as they become part of the extreme matter that exists at the white dwarf's photosphere. At these pressures and temperatures, ordinary matter cannot exist in familiar forms. The electromagnetic forces that create atoms and molecules are overwhelmed by the extreme conditions. Our traveler's constituent particles, the protons, neutrons, and electrons that once formed atoms, join to degenerate matter. That comprises the white dwarf's structure. In the quiet space of quantum mechanics, these particles find new arrangements dictated by the Pauli exclusion principle. Electrons, no longer bound to specific nuclei, form a degenerate electron gas that provides the pressure support, keeping the white dwarf from collapsing further. The nuclei, stripped of their electrons, pack together at densities approaching those found in atomic nuclei themselves. Gently, we discover that our traveler S atoms have become part of a new form of matter-degenerate matter, where quantum effects dominate over thermal effects. In this state, matter behaves more like a quantum fluid than like ordinary gas, liquid, or solid. The pressure that supports the white dwarf against further gravitational collapse comes not from thermal motion, but from the quantum mechanical requirement that electrons occupy different energy states. This transformation represents a return to cosmic unity. The elements that once comprised our traveler carbon, oxygen, nitrogen, and trace amounts of heavier elements are the products of stellar nucleosynthesis forged in the cores of previous generations of stars. Now, in their encounter with the white dwarf, these elements join a stellar remnant that represents the final stage of stellar evolution for stars like our Sun. As our journey continues into the deepest contemplation of this process, we can appreciate that what has happened to our traveler is, in a cosmic sense, a homecoming. The matter that formed their hypothetical body originated in stellar cores was dispersed into space. Through stellar winds and planetary nebulae coalesced into planets and eventually into complex structures capable of consciousness and has now returned to a stellar remnant. This cycle from stellar cores to interstellar space to planets to life and back to stellar remnants represents one of the fundamental cycles of cosmic evolution. Matter flows through these different states over billions of years, sometimes forming stars, sometimes planets, sometimes living beings, and sometimes the exotic states we find in white dwarfs. Now we float toward understanding the broader implications of our thought experiment. What does it mean to fall into a white dwarf in the context of cosmic evolution, and the fate of matter in the universe? White dwarfs represent stable endpoints for stellar evolution, unlike neutron stars, which can accrete matter and potentially collapse into black holes, or black holes themselves, which eventually evaporate through Hawking radiation. White dwarfs can exist in their current form for trillions of years, far longer than the current age of the universe. The matter that comprises our white dwarf, including the atoms that once formed our hypothetical traveler, will remain in this degenerate state for eons. Over time scales so vast that they dwarf even geological time, the white dwarf will gradually cool, its surface temperature dropping from tens of thousands of degrees to thousands, then hundreds, and eventually approaching the temperature of the cosmic microwave background itself. In the quiet space of deep cosmic time, our white dwarf will eventually become a black dwarf, a cold, dark stellar remnant no longer glowing with thermal radiation. But even this is not the end of the story. Over time scales that make the current age of the universe seem like an instant, even the protons that comprise the white dwarf's nuclei may decay, finally returning their constituent energy to the cosmic background. But these time scales are so vast, 1034 years or more, that they exist more in the realm of theoretical physics than practical consideration. For all intents and purposes, the white dwarf represents a stable, peaceful repository for the matter of the universe, a place where atoms can rest in exotic but stable configurations for times longer than human imagination can easily grasp. Like whispers in the night, white dwarfs tell us stories about the ultimate fate of matter in an expanding universe. As the cosmos continues to grow and cool, stars will eventually exhaust their nuclear fuel and evolve into white dwarfs. If they're not to massive neutron stars or black holes, the era of star formation will eventually end as available gas is consumed, or dispersed beyond the reach of gravitational collapse. In this far future, white dwarfs will be among the last objects to shine in the universe, slowly cooling remnants of a more active epoch when nuclear fusion powered the cosmos. They will serve as cosmic lighthouses, marking the locations where once magnificent stars completed their evolutionary journeys. As our journey continues through these cosmic contemplations, let's drift into considering what our thought experiment teaches us about the nature of matter and energy. The extreme conditions near and within white dwarfs reveal aspects of physics that cannot be studied in terrestrial laboratories. The degenerate matter that comprises white dwarfs exists in a state where quantum mechanics dominates over classical physics. This is a realm where the wave-like nature of matter becomes more important than its particle-like properties, where the uncertainty principle creates pressures that can support the mass of an entire star, and where the distinction between matter and energy becomes beautifully blurred. Gently, we discover that white dwarfs serve as natural laboratories for studying physics under conditions of extreme density, temperature, and magnetic field strength. The spectral lines we observe from white dwarfs are shifted and split by gravitational fields and magnetic effects that are impossible to replicate on Earth, providing unique insights into the fundamental laws of nature. The crystallization of white dwarf cores, a process that occurs as these objects cool over billions of years, creates some of the largest crystals in the universe. These crystals, composed of carbon and oxygen nuclei arranged in regular lattices, represent a state of matter where the boundary between liquid and solid is defined by quantum mechanical rather than thermal effects. In the quiet space of these extreme conditions, white dwarfs also serve as precision cosmic clocks. Their cooling rates are so predictable that astronomers can use white dwarf temperatures to estimate the ages of stellar populations, and even to place constraints on the age of the universe itself. The magnetic fields of white dwarfs, some of the strongest known in the cosmos, create laboratory conditions for studying magnetized plasma under extreme conditions. These fields can channel material flow, create cyclotron radiation, and influence the structure of the white dwarf's atmosphere in ways that provide insights into magnetohydrodynamics and plasma physics. Now we float toward contemplating the role of white dwarfs in the cosmic ecology. Far from being mere stellar endpoints, white dwarfs play active roles in the ongoing evolution of galaxies and the enrichment of the interstellar medium with heavy elements. Some white dwarfs exist in binary systems where they can accrete material from a companion star. This accretion process, while gentle and gradual, can lead to remarkable phenomena. As material spirals down onto the white dwarf's surface, it forms an accretion disk that glows brilliantly in X-rays and ultraviolet light. Periodically, the accumulated material on the white dwarf's surface can undergo thermonuclear explosions, called nevae. These events, while dramatic by astronomical standards, are relatively gentle compared to supernovae, and they serve to enrich the surrounding space with newly synthesized elements, while leaving the white dwarf itself largely intact. In rare cases, if a white dwarf in a binary system accumulates enough mass to approach the Chandrasekhar limit, about 1 point for solar masses, it can undergo a catastrophic thermonuclear explosion, called a Typeus supernova. These events, while marking the end of the white dwarf, serve as standard candles for measuring cosmic distances and played a crucial role in the discovery of the accelerating expansion of the universe. Like whispers in the night, these Typeus supernovae also serve as cosmic alchemists, synthesizing iron peak elements like nickel, cobalt, and iron itself, and dispersing them throughout the galaxy. The iron in our blood, the nickel in coins, and many other elements essential for life were likely forged in the final moments of white dwarf explosions billions of years ago. As our journey continues through these cosmic cycles, we can appreciate how our hypothetical traveler S-fall into a white dwarf connects to the broader story of cosmic evolution. The atoms that once formed stars, planets, and perhaps living beings continue their cosmic journey through different states of matter, different gravitational environments, and different physical conditions. In the quiet space of this perspective, death and transformation become part of a larger cosmic dance. Nothing is truly lost. Matter and energy are conserved, changing form but never disappearing. Our traveler's atoms, now part of the white dwarf's degenerate matter, carry within them the history of previous stellar generations and the potential for future cosmic adventures. Let us drift into contemplating the observational evidence for white dwarfs and what they tell us about stellar evolution and cosmic history. The first white dwarf discovered, Sirius B, was identified in 1862 as the invisible companion to the bright star Sirius. This discovery revolutionized our understanding of stellar evolution and revealed the existence of extremely dense forms of matter. Since then, astronomers have identified thousands of white dwarfs in our galaxy and beyond. These observations have confirmed many of the theoretical predictions about stellar evolution and provided insights into the masses, compositions, and ages of stellar populations. The white dwarf population in our galaxy tells a story written in the language of stellar astronomy. The distribution of white dwarf masses reflects the distribution of progenitor star masses, while their cooling ages provide information about the star formation history of our galactic neighborhood. Gently, we discover that white dwarfs also serve as archaeological tools for studying the early universe. The oldest white dwarfs, with cooling ages of 12 to 13 billion years, formed when the universe was much younger and had a different chemical composition. These ancient stellar remnants carry information about conditions in the early cosmos, locked within their crystallized cores. The study of white dwarfs has also contributed to our understanding of fundamental physics. Measurements of white dwarf masses and radii provide tests of the equation of state for degenerate matter, while observations of cooling white dwarfs place constraints on exotic physics, like axion production and neutrino properties. Pulsating white dwarfs, known as ZZ Ceti stars, undergo regular brightness variations caused by non-radial pulsations in their surface layers. These stellar seismology studies allow astronomers to probe the internal structure of white dwarfs, much like how earthquake waves reveal Earth's internal structure. Now we float toward considering white dwarfs in the context of astrobiology and the potential for life in the universe. While white dwarfs themselves are far too hot and dense to support life as we know it, they may play important roles in the cosmic story of biological evolution. The heavy elements essential for life, carbon, oxygen, nitrogen, phosphorus, sulfur, and others are produced in stellar cores and dispersed into space when stars evolve and shed their outer layers. White dwarfs represent the final resting places for these stellar cores, but the material they shed during their formation becomes part of the interstellar medium, from which new stars and planets form. In this sense, white dwarfs are cosmic recycling centers, processing stellar material and making it available for future generations of stars and planets. The planetary nebulae that surround newly formed white dwarfs are among the most beautiful objects in the universe, but they also serve as distribution mechanisms for the elements of life. Some research has suggested that planets might survive the evolution of their host stars into white dwarfs orbiting these stellar remnants at large distances. Such planets would be cold and airless, but they might retain subsurface oceans heated by radioactive decay or tidal forces. Whether life could persist in such environments remains an open question, but it illustrates the potential for white dwarfs to play roles in cosmic biology that we are only beginning to understand. In the quiet space of these considerations, we can appreciate how our thought experiment about falling into a white dwarf connects to the largest questions about life, the universe, and our place within it. The same physical processes that would transform our hypothetical traveler also created the elements, from which we are made and will continue to shape the cosmic environment in which future life might emerge. Like whispers in the night, white dwarfs remind us of the deep connections between stellar evolution, planetary formation, and the emergence of complexity in the universe. They are both endpoints and waypoints in the cosmic journey of matter from simplicity to complexity, and back again. As our journey continues through these final contemplations, let's drift into considering what our white dwarf thought experiment teaches us about the nature of time, space, and existence itself. The extreme gravitational conditions near white dwarfs create environments where the predictions of Einstein's general relativity become directly observable. The time dilation experienced by our hypothetical traveler illustrates one of the most profound insights of modern physics that time is not absolute and universal, but relative and dependent on gravitational fields and relative motion. Near the white dwarf, time literally passes more slowly, creating a situation where simultaneity becomes meaningless between different locations. This relativity of time has philosophical implications that extend far beyond physics. It suggests that the universe is for stranger and more wonderful than our everyday experience suggests, with different observers experiencing different flows of time depending on their gravitational environment and state of motion. the curvature of space-time near the white dwarf also demonstrates that space itself is not a fixed stage on which physics plays out, but rather a dynamic participant in cosmic events. The geometry of space responds to the presence of matter and energy, creating the gravitational effects that guide the motion of our traveler and shape the structure of the universe on the largest scales. Gently, we discover that these insights from general relativity connect to deeper questions about the nature of reality itself. If space and time can be curved, stretched, and dilated, what does this tell us about the fundamental nature of existence? Are space and time fundamental aspects of reality, or are they emergent properties of something even more basic? White dwarfs, as extreme laboratories for testing general relativity, provide glimpses into these deep questions. The fact that Einstein's century-old theory continues to make accurate predictions in these extreme environments suggests that we have identified something fundamental about the structure of reality, yet the theory also predicts its own limitations in even more extreme environments. In the quiet space of these contemplations, we can appreciate how our simple thought experiment about falling into a white dwarf opens windows into some of the deepest questions in physics and philosophy. What is the nature of matter and energy? How do space and time relate to physical reality? What is the ultimate fate of complexity in an expanding universe? These questions may not have final answers, but the process of exploring them through thought experiments like ours, through careful observations of white dwarfs and other cosmic phenomena, and through the development of theoretical frameworks that can make sense of these observations, represents one of humanity's greatest intellectual achievements. Now we float toward the peaceful conclusion of our cosmic journey. Our hypothetical traveler, having experienced the ultimate transformation possible in the vicinity of a white dwarf, has become part of one of the universe's most stable and long-lived objects. Their atoms, once part of a conscious being contemplating the cosmos, now exist in the exotic state of degenerate matter, held in equilibrium by quantum mechanical forces. This transformation, while representing the end of our traveler's individual existence, also represents their integration into the cosmic story on the largest scales. The white dwarf that now contains their matter will continue to shine for trillions of years, gradually cooling but remaining largely unchanged until the universe itself has evolved beyond recognition. In this sense, our thought experiment illustrates both the fragility and the persistence of matter in the universe. Individual structures, whether planets, stars, or living beings, form and dissolve on cosmic timescales, but the matter and energy from which they are made continues on, taking new forms and participating in new cosmic adventures. The elements that once formed our traveler will remain locked in the white dwarf's crystalline core, perhaps for times longer than the current age of the universe. They will be witnesses to the continued expansion of the cosmos, the formation and evolution of new generations of stars and galaxies, and possibly the emergence of new forms of complexity and consciousness that we cannot yet imagine. Like whispers in the night, these transformed atoms carry within them the history of cosmic evolution, from the primordial nuclear synthesis that created the lightest elements in the early universe, through the stellar furnaces that forged heavier elements, to the planetary environments where complexity and perhaps consciousness emerged, and finally to their current state as part of a stellar remnant. This journey from cosmic simplicity to complexity and back toward simplicity represents one of the fundamental patterns of cosmic evolution. It suggests that the universe is engaged in a vast exploration of possibility, trying out different configurations of matter and energy, different structures and processes, different forms of organization and complexity. As our journey continues through these final reflections, we can appreciate how our white dwarf thought experiment connects to the human story and our own place in the cosmic narrative. We are made of stellar material, the calcium in our bones, the iron in our blood, the oxygen in our lungs were all forged in stellar cores and dispersed into space, through processes similar to those that created our white dwarf. In contemplating the fate of our hypothetical traveler, we are also contemplating our own cosmic origins and ultimate destiny. We are temporary arrangements of matter and energy that have achieved the remarkable property of self-awareness, capable of contemplating our own existence and our place in the universe. This self-awareness allows us to participate consciously in the cosmic story, to understand our connections to stars and galaxies, to appreciate the deep time scales on which cosmic evolution operates, and to feel wonder at the remarkable complexity that can emerge from simple physical laws operating over vast scales of space and time. Gently we discover that our thought experiment about falling into a white dwarf is ultimately a meditation on existence itself, on what it means to be a conscious part of the universe, on how individual existence relates to cosmic processes, and on how awareness and understanding can provide meaning even in the face of ultimate physical transformation. The peaceful nature of our traveler's transformation, stretched gently by tidal forces, heated gradually by intense radiation, and finally integrated into the exotic matter of the white dwarf, reflects the fundamental character of cosmic processes. While often extreme by human standards, these processes follow natural laws and unfold according to principles that can be understood through careful observation and theoretical development. In the quiet space of this understanding, even the most extreme cosmic phenomena, the collapse of stellar cores, the formation of degenerate matter, the warping of space and time, become sources of wonder rather than fear. They represent the universe exploring the full range of possibilities available within the framework of physical law. Our white dwarf, glowing peacefully in the cosmic dark with the stored thermal energy of its former stellar life, serves as a beacon of stability in an ever-changing universe. It will continue to shine long after our sun has exhausted its nuclear fuel and evolved through its own stellar death. Long after the Milky Way has merged with neighboring galaxies, long after most of the universe's stars have completed their nuclear burning phases. Now we float toward our final contemplations about the cosmic significance of white dwarfs and what they teach us about the universe's long-term evolution. In the far future, when star formation has ceased and the universe has expanded and cooled to the point where nuclear fusion no longer occurs, white dwarfs will be among the last sources of energy in the cosmos. These slowly cooling stellar remnants will provide islands of warmth in an increasingly cold and dark universe. Any hypothetical civilizations existing in that distant future might cluster around white dwarfs, harvesting their thermal energy as they gradually radiate away, the last vestiges of stellar nuclear synthesis. Even farther in the future, when the white dwarfs themselves have cooled to the temperature of the cosmic microwave background, they will persist as dark, crystalline objects, cosmic diamonds containing the compressed matter of entire stars. They will serve as monuments to the era when the universe was young and energetic enough to support nuclear fusion and stellar evolution. In the unimaginably distant future, when proton decay, if it occurs, has dissolved even these stellar remnants, the matter that once formed our white dwarf and our hypothetical traveler will have returned to the cosmic background as individual particles and radiation. The universe will have completed a vast cycle from simplicity to complexity and back to simplicity, but at a higher level of organization, having explored through its evolution the full range of possibilities available within the constraints of physical law. Like whispers in the night, these ultimate time scales remind us of the temporary nature of all structure in the universe, while simultaneously highlighting the remarkable fact that the universe has given rise to structures complex enough to contemplate their own existence and ultimate fate. This capacity for self-reflection embodied in conscious beings like ourselves, who can imagine falling into white dwarfs, understand the physics involved, and contemplate the cosmic implications, represents one of the universe's most remarkable achievements. Through us, and perhaps through other conscious beings elsewhere in the cosmos, the universe has developed the ability to understand itself. As our journey continues through these deepest contemplations, we can appreciate that our thought experiment serves multiple purposes. On one level, it provides a vehicle for exploring the fascinating physics of white dwarfs, extreme gravitational fields, and the behavior of matter under conditions impossible to replicate on Earth. On another level, it serves as a meditation on cosmic evolution, stellar life cycles, and the fate of matter and energy in an expanding universe. It connects individual existence to cosmic processes and helps us understand our place In the vast scales of space and time, on the deepest level, it represents an exercise in cosmic empathy, the ability to imagine ourselves in radically different physical environments and to understand how the laws of physics would shape our experience in those environments. This imaginative capacity is one of the unique gifts of consciousness, allowing us to transcend the limitations of our immediate physical situation and explore the full range of cosmic possibilities. Gently, we discover that this exercise in cosmic empathy connects us more deeply to the universe of which we are a part. By imagining the experience of falling into a white dwarf, we develop a more intimate understanding of gravity, space-time, quantum mechanics, and stellar evolution. We come to appreciate these not as abstract theories, but as aspects of the cosmic environment that shapes all existence. This deeper understanding, in turn, enhances our sense of wonder and connection to the cosmos. We begin to see ourselves not as separate from the universe, but as expressions of it, temporary arrangements of cosmic material that have achieved the remarkable property of self-awareness and the ability to understand the processes that created us. In the quiet space of this cosmic perspective, the transformation of our hypothetical traveler becomes a metaphor for the transformation of consciousness itself through the process of understanding. Just as our traveler's matter becomes integrated into the exotic structure of the white dwarf, our understanding becomes integrated into the larger framework of cosmic knowledge. This integration represents a form of transcendence, not escape from physical reality, but deeper engagement with it. Through understanding, we become more fully ourselves while simultaneously recognizing our fundamental unity with the cosmic processes that gave rise to us. The white dwarf that serves as the focus of our thought experiment embodies this unity of individual and cosmic scales. It contains the matter of an entire star compressed into an Earth-sized volume, representing both the ultimate expression of gravitational collapse and a stable endpoint that can persist for cosmic ages. In its crystalline core, carbon and oxygen nuclei arrange themselves in perfect lattices, creating some of the largest and most perfect crystals in the universe. These structures represent a kind of cosmic order emerging from the chaotic processes of stellar evolution, beauty and symmetry arising naturally from the operation of physical law. Now we float toward the gentle conclusion of our cosmic meditation. Our journey has taken us from the vast scales of interstellar space, through the increasingly extreme environments near a white dwarf, to the ultimate transformation of matter in the stellar remnants' degenerate interior. Along the way, we have explored the physics of gravity, relativity, quantum mechanics, and stellar evolution. We have contemplated the role of white dwarfs in cosmic evolution, their contribution to the chemical enrichment of the universe, and their potential significance for the long-term fate of matter and energy in an expanding cosmos. Most importantly, we have used our thought experiment as a vehicle for developing a deeper appreciation of our place in the cosmic story. We have come to understand ourselves as temporary arrangements of stellar material that have achieved consciousness and the ability to contemplate the universe that created us. This understanding brings with it both humility and wonder. Humility, because it reveals the vast scales of space and time on which cosmic evolution operates, making our individual lives seem like brief flickers in the cosmic dark. Wonder, because it reveals the remarkable complexity and beauty that can emerge from simple physical laws operating over cosmic scales. The white dwarf at the center of our thought experiment embodies both of these aspects. It represents the ultimate fate of individual stars like our Sun, yet it also represents a stable form that can persist for longer than the stars from which it formed. It is both an ending and a beginning, the end of nuclear fusion and stellar activity, but the beginning of a new phase of cosmic evolution that will extend far into the future. Like whispers in the night, white dwarfs remind us that the universe is full of wonders that exist on scales and in forms that transcend our everyday experience. They challenge us to expand our imagination, to think beyond the familiar, and to appreciate the remarkable diversity of physical phenomena that emerge from the simple laws that govern cosmic evolution. As our contemplative journey draws to its peaceful close, we can appreciate how our simple thought experiment has opened windows into some of the deepest questions about existence, consciousness, and our place in the universe. These questions may not have final answers, but the process of exploring them enriches our understanding and deepens our connection to the cosmos. The transformation of our hypothetical traveler from conscious being to exotic matter serves as a reminder that consciousness itself is one of the universe's most remarkable emergent properties. Through consciousness, the universe has developed the ability to contemplate itself, to understand its own processes, and to appreciate its own beauty and complexity. This capacity for self-reflection and understanding represents a form of cosmic awakening, the universe becoming aware of itself through the consciousness of the beings it has created. In this sense, our exploration of what it means to fall into a white dwarf is also an exploration of what it means for the universe to understand itself. In the quiet space of this understanding, we find a deep peace that comes from recognizing our fundamental unity with the cosmic processes that created us. We are not separate from the universe looking in from the outside, but expressions of the universe exploring its own possibilities from the inside. This perspective transforms our relationship with existence itself. Death and transformation become part of the cosmic dance rather than endings to be feared. Individual consciousness becomes a temporary manifestation of the universe's capacity for self-awareness rather than an isolated phenomenon, struggling against hostile forces. The white dwarf, slowly cooling in the cosmic dark, serves as a symbol of this deeper understanding. It represents matter that has found a stable form after the drama of stellar evolution, content to shine peacefully for eons with the stored energy of its former fusion reactions. In its patient existence, we can find a model for our own relationship with time and change. Like the white dwarf, we can find peace in understanding our place in the cosmic story, appreciating both the temporary nature of our individual existence and our participation in processes that extend far beyond our individual lifespans. Gently, we discover that this cosmic perspective brings with it a sense of profound gratitude. We are remarkably fortunate to exist at a time and place in cosmic history when complexity has emerged to the point where conscious beings can contemplate the universe that created them. We are witnesses to the cosmic story unfolding, participants in the universe's ongoing exploration of its own possibilities. This gratitude extends to the white dwarfs themselves, those peaceful stellar remnants that will outlive us by trillions of years. They serve as cosmic lighthouses, marking the locations where magnificent stars once burned, and they will continue to serve as landmarks in the cosmic geography, long after our own sun has evolved through its stellar life cycle. In their gentle glow, we can see reflected the entire history of cosmic evolution, from the first stars that formed in the early universe, through the complex chemistry that created the elements essential for life, to the planetary environments where consciousness emerged and began to contemplate its own existence. As our meditative journey reaches its natural conclusion, we return to where we began, floating peacefully in the vast cosmic ocean, surrounded by the gentle light of countless stars, many of which will eventually become white dwarfs themselves. Our thought experiment about falling into one of these stellar remnants has served as a vehicle for exploring not just the physics of extreme gravitational environments, but the deeper questions about existence, consciousness, and our place in the cosmic story. The white dwarf continues its patient existence, slowly cooling but remaining stable for times that dwarf human imagination. In its crystalline core, the matter that once formed our hypothetical traveler rests in exotic configurations that will persist long after the galaxies themselves have evolved beyond recognition. This persistence represents a form of cosmic memory, the white dwarf serving as a repository for the matter and energy that once participated in stellar fusion, planetary formation, and perhaps even biological evolution. In its degenerate matter, the history of cosmic evolution is preserved in a form that can survive the vast changes that lie ahead in the universe's future. Like whispers in the night, this cosmic memory reminds us that nothing is ever truly lost. Matter and energy change form, but they continue to participate in the ongoing evolution of the universe. Consciousness may be temporary, but the understanding it achieves becomes part of the cosmic story, influencing how the universe continues to evolve and explore its own possibilities. In this sense, our exploration of what it means to fall into a white dwarf becomes a celebration of consciousness itself, of the remarkable fact that the universe has given rise to beings capable of understanding their own cosmic origins and contemplating their ultimate fate. Through this understanding, we transcend the limitations of our individual existence and connect with the eternal processes that govern cosmic evolution. The white dwarf, glowing peacefully in the cosmic dark, serves as a symbol of this transcendence. It has moved beyond the active phase of stellar evolution into a state of stable equilibrium that can persist for eons. Similarly, through understanding, we can move beyond the anxieties and limitations of everyday existence into a state of peaceful appreciation for our place in the cosmic story. This appreciation brings with it a deep sense of wonder that can transform our relationship with existence itself. We begin to see ourselves not as isolated individuals struggling against hostile forces, but as expressions of the universe's creativity, temporary manifestations of its ongoing exploration of complexity and consciousness. In the quiet space of this understanding, we find a peace that transcends individual concerns and connects us with the eternal rhythms of cosmic evolution. We become part of the universe's contemplation of itself, participants in its ongoing journey of discovery and understanding. The transformation of our hypothetical traveler from conscious being to exotic matter within the white dwarf represents the ultimate expression of this cosmic participation. Even in the most extreme physical transformation imaginable, the matter and energy that once formed individual consciousness continues to play a role in the cosmic story. This continuity suggests that consciousness itself may be more fundamental than we typically assume, not an accidental byproduct of cosmic evolution, but an expression of the universe's inherent tendency toward complexity, organization, and self-awareness. Through consciousness, the universe develops the ability to understand and appreciate its own beauty and complexity. As we conclude our gentle exploration of this cosmic thought experiment, we can appreciate how it has served multiple purposes. It has introduced us to the fascinating physics of white dwarfs and extreme gravitational environments. It has connected individual existence to cosmic processes and helped us understand our place in the vast scales of space and time. Most importantly, it has served as a meditation on the nature of existence itself, helping us develop a deeper appreciation for the remarkable fact that we exist at all in a universe capable of giving rise to complexity, consciousness, and understanding. The white dwarf continues its peaceful existence, slowly cooling but remaining stable, a cosmic lighthouse marking the location where a magnificent star once burned. In its patient glow, we can see reflected the entire cosmic story, from the first moments after the Big Bang through the formation of the first stars and the creation of the elements essential for life to the emergence of consciousness and the development of understanding. This story is our story, for we are expressions of the same cosmic processes that created the white dwarf. The elements in our bodies were forged in stellar cores. The energy that powers our thoughts comes from fusion reactions in our sun, and the physical laws that govern our existence are the same ones that determine the structure and evolution of white dwarfs. In recognizing this cosmic unity, we find a profound sense of belonging that transcends the apparent isolation of individual existence. We are not separate from the universe but expressions of it, temporary arrangements of cosmic material that have achieved the remarkable property of self-awareness. This self-awareness allows us to participate consciously in the cosmic story, to understand our connections to stars and galaxies, and to appreciate the deep beauty and complexity that emerge from simple physical laws operating over vast scales of space and time. The white dwarf, in its stable serenity, serves as a reminder that this cosmic story will continue long after our individual participation has ended. The matter and energy that currently form our bodies will continue their cosmic journey, taking new forms and participating in new adventures that we cannot yet imagine. In this continuity, we find both humility and comfort. Humility, because it reminds us that individual existence is temporary and small compared to cosmic scales. Comfort, because it assures us that we are part of something larger and more enduring than ourselves. The peaceful glow of the white dwarf, slowly cooling in the cosmic dark, embodies this eternal aspect of cosmic evolution. It will continue to shine for trillions of years long after our Sun has evolved through its own stellar life cycle, long after the Milky Way has merged with neighboring galaxies, long after most of the universe's stars have completed their nuclear burning phases. In its patient existence, we can find a model for our own relationship with time and mortality. Like the white dwarf, we can find peace in understanding our place in the cosmic story, appreciating both the temporary nature of our individual existence and our participation in processes that extend far beyond our individual lifespans. This cosmic perspective brings with it a deep serenity that comes from recognizing our fundamental unity with the processes that created us. We are not struggling against the universe but expressing its creativity. We are not separate from cosmic evolution but part of its ongoing exploration of complexity and consciousness. As our gentle journey through this cosmic thought experiment draws to its natural close, we return to the peaceful state with which we began floating in the vast cosmic ocean, surrounded by the gentle light of countless stars, many of which will eventually become white dwarfs themselves. Our exploration of what it means to fall into a white dwarf has taken us on a journey through the extremes of physics and the depths of cosmic philosophy. We have contemplated the transformation of matter under extreme conditions, the relativity of space and time, and the role of consciousness in the cosmic story. Most importantly, we have developed a deeper appreciation for the remarkable fact that we exist at all in a universe capable of giving rise to complexity, beauty, and understanding. Through our capacity for wonder and contemplation, we participate in the universe's ongoing journey of self-discovery. The white dwarf continues its peaceful existence, a cosmic lighthouse in the vast dark, slowly cooling but remaining stable for times that transcend human imagination. In its patient glow, we can see reflected the entire cosmic story of which we are a part, and in that reflection, we find both the humility that comes from recognizing our place in the vast cosmos, and the wonder that comes from understanding our remarkable capacity to contemplate the universe that created us. Good night from the sleepy scientist.